So somebody else, yeah.
From 11.5, I was wondering if you could do one of the graphing ones, like 21 through 28.
Oh, and for this, let me pull this up here semi-quickly. I think I showed you this. I can't remember now. Did I show you an example of isometric paper?
Yeah.
Yes. Oh, good. Okay, so I'll just pull it up in case. So if you haven't done this for yourself yet, I would definitely go online, type into Google isometric paper images, and it'll come up with, and I'll show it to you again. And I might be able to put it up here if I'm lucky. I'll try to do it right here. We'll see what happens.
I have one if you want to.
Oh, thank you. You're willing to just give it to me?
Yeah, sure.
You're a nice person. Thank you. Okay. Let me see. I think it'll be all right. Cool. Now, 21, it's the 3D ones that's going to give you trouble, right? 21, what plane is that? In number 21 it says cosine Ti plus sine Tk. XZ. You don't truly need this. It exists in just the XZ plane. Do you understand? So you can actually do any 2D. You can just do a 2D. You just have to identify the axes, X, Z. There's no need to put it on a 3D, because then you're just looking at 2D thing from the side, and that's just silly.
Right. Do the hard one then, not one?
Yeah, we'll do one that's a 3D one.
So like if you're just doing the XZ plane, do you just draw it like you would normally do an XY?
Oh yeah.
Change the...
Yeah. Because it entirely exists in that plane. There's no way it can step off that plane, right? Because it's plus 0j. So it can't go in the j direction at all. So it's got to exist only on that plane. So let's do one that's not like that.
Will you show us graph paper if you have to graph them?
Oh yeah.
Will it be the isometric?
Oh yeah. Yeah. It would be kind of evil. Yeah. No, I'll provide you with like a little thing about this big, because I'm not going to ask you to do like crazy things, but I'll give you something like this. Of course, that looks huge just because I'm zoomed in, but and you can do it on there. So let's do one of these problems like it doesn't really matter here. Let me zoom out a little bit. Okay. So you found this where, Miss? Did you?
So I go those.
Yeah, you. Okay, good. Good. All right. It's just the cost of paper from Office Depot. So if we look at like, I don't know, doesn't truly matter. This one. 2 cosine t I hat plus 2 sine t j hat plus sine t k hat. Okay? Yeah. If I took the k hat part out, what image would that create? I mean, what? Circle, right? In fact, can anybody tell me something interesting about that circle?
Circle with radius 2.
Good, radius 2, because the factor of 2 in there. Cool? Because each one of them are going to go out to at most 2. So in the x direction, 2, negative 2, 2, negative 2. You get a nice little radius 2 circle. What does that k addition do to it then? So in a later section, we're going to be doing a bit more three-dimensional plotting.
Wouldn't it look like a saucer?
So okay, so now you're thinking ahead. We're going to be doing something where it's going to be important for us to know what does it look like in each of the 2D cuts. If I know what it looks like on the XY plane, what it looks like XY plane, what it looks like in the XZ plane, what it looks like in the YZ plane, I can try to put those together. And normally I think of it like chicken wire. I can almost see a structure coming out of it. You guys are art majors or like art. Chicken wire, you throw some plaster Paris crap on there, and so you normally put the structure down in each dimension, and then you try to fill it in. Some of us are better than others at art and drawing. I'm not, so I will be pretty lenient. As long as I can see some of your work, you'll be fine. This one's not too bad. They give us from, this is number, where'd it go? 24, yeah. And they tell us that t is between 0 and 2 pi. So what I did was, and that's why I was saying that, I looked at it just in that plane. Right, taking out the k, taking out the z, so I only got the xy plane. And then I think, well, what would that do to that image? In the xy plane, it would be a circle if it only had to exist there. But now what's that circle basically going to do? It's going to go up and then down from there, right? So it's going to be above and below that based on the output for sine t. If I just made that plus tk, no sign, just plus tk, what would that do to the circle? You kind of just lift it up, right? So it'd be sort of like a spring. It would go out like this. And there's actually an example of that in the book, in this section. Okay. Yes, cool. So for this, what do you think you should start off doing? Let's actually do the first step, and then we'll see how to plot this. All right, cool. So we can attack this first. So I'm going to make this. I should bring a ruler with me. That'll be my z-axis. Let's make this my. Yeah, Jeff, you can follow a line. There you go. My y-axis. This will be my x-axis. Let's see. Do you see how this helps now? I mean, when you first see that and you haven't drawn anything, you're like, what the hell good is that shit going to do for me? Because you might be looking at a 2D. But now you can see sort of how the 3D, maybe you can. It's not the best, but oh well. Make those axes really pop out. That's good? You guys can see that? Okay. Thank you. So now, here's the cool thing about plotting a point. So let's create a few points. All right, so I am going to look at them as points. They are actually, this officially is what's called a vector value function. You have inputs and the outputs are going to be vectors. But I'm just going to be plotting the points. It would get really messy if I'm trying to eternally plot all the vectors in there. That would definitely suck. So I'm just going to plot the points that this thing is going to be pointing to. So if t is 0, what do I get? 2, 0, 0. So to plot the point 2, 0, 0. Here's 1, 2 in the x-axis, and that's easy. All right, that's exciting. So let's get to something a little more interesting. All right, so there's 2 on the x-axis. Is that cool? Okay. So now if I plug in there pi over 6, let's say. Haha. Root 3, okay. So that one must be 1. 1/2. I like it. Root 3 is roughly 1 point something. Okay. So we got root 3. So 1 point. So here's 1.27. And then 1 on the y-axis. So I got to 1. I don't know, guys, are you guys able to follow me there? So this is really, once you set your axes up, this paper makes it so much easier to plot this stuff. I know some of you guys are pretty artistic. I can tell from what you've done. I guess I should be getting this. But I'm not. I think you can tell that. So I try to draw freehand the little plane sitting out there, that I would die on that. But this paper makes it relatively easy. Poor little dude. There you go. I'm not sure, you probably can't see that at all, but that's all right. So here I am. So root 3 is roughly there. 1 on the y-axis. And then 1/2. And now watch how this works on the z-axis. So here I am. Actually, I should probably do the 1/2 first. So I can go root 3. 1/2 would be right here, wouldn't it? On the z. And then if I follow, now see how I can kind of follow where I am on the y-axis. I want to go 1 over. So here I am. Root 3, 1. And then over 1 on the y-axis. So let me see where I end up. Let me zoom in on this. Shoot. So let's see. Root 3, 1/2 up, and then 1 over on the y-axis would be roughly right there. And then you can keep going. Put in there pi over 4, so forth. So with regular graph paper, 3D drawing would be basically impossible, especially for a more complicated thing than just a plane. So I would definitely, this is actually a decent size to get. 2-on-1, where you can do a full graph on one and a full graph on the other one, but you're not wasting a lot of paper. Right? So this would be one problem, another problem here. And it was pretty easy to find, right? Just type in there isometric. Isometric. Cool. So just do, and you keep going. You can kind of connect the dots as you go. Yes, ma'am.
Okay, I'm having trouble seeing. To me, that looks like it would be -1/2 on the z-axis.
So if you go, let me see, where'd I go? So √3, yes, the angle.
You got a picture like going up or coming up?
Let's try a point here. Let's just try a point. Let's try one that's a little further out because it's getting kind of close to there.
We use dotted lines to show that we're going out.
Yeah. But that's not, you don't have to do that on this because if you do dotted lines, it's going to get a little full of stuff. It's going to look like it's got measles. So let's try one that's a little bit easier to see. Let's try 1, 5, 3. So if I go 1, 5, 1, 2, 3, 4, 5, and then 3, 1, 2, 3. There it is, right?
That's actually better.
Yeah, so it's a little hard because it's close to the axes back here. So √3, 1, and then you got a nice block here, right? So 1/2 would actually be even lower than where I put it. I don't know if you guys can, let me see.
Oh yeah.
Right here, let's see real quick, right here. Let me just do this real quick right here. I want you guys, that's awesome, Jeff. Okay. All right, right here. So let's just look at √3. Let's just look at √3, 1, 1/2. √3 would be right here. 1 is here. And now look, you've got this square here to work with. You see that? You got this square here? There you go. So √3, 1, and then see this square? You just go up halfway in that square.
Oh yeah.
So each point, each direction has its own little square to kind of work with. So if I want to go up 1, you go up a full square. So √3, 1, and then 1/2 is just halfway up this square here. Do you see that? Mm-hmm. Sort of. And that's better. But that's where we got to start. So if I had to go √3, 1.1, it'd be like right there, just barely up in the square. So the bottom of the square is z equal to 0, right? I'm in the xy plane. And the top of the square is equal to 1. Right? So now if I want to go up 1/2, there I am. Now the reason you have to think 3D, which this paper makes it a little easier to do, but I'm not saying it makes it easy to do. So right here you got to realize you might think we're below or something, but we know we're not. I mean, and again, a point by itself in 3D is really hard to tell. If I just put a point there, where is that? Yeah.
I kind of see why he thought it would be -1.
No, and of course I can too.
Why isn't it like above that? Because I mean, if you try to make the plane.
Because look here, right there. What is z right there? What value would z have at that point? 0. Now, looking at it, doesn't it look like it's below? But we know it's on this axis. So right here, this point right there, what's the value of z right there, knowing how we got there?
0.
So to go 1/2, I go up half, wouldn't I?
Yeah.
Now, unfortunately, it is very confusing, right? And that's why we have things such as optical illusions and all that, because it's really easy to confuse our eyes. Because depth perception and all that kind of business is really easy to play with that, right? And movies do it all the time. Look at the movie Elf. Or if you just, Elf's funny. But that's why that point, it looks like it could be in a lot of different places, but we know where it is. We know where it is. And if you want to, you can draw your little dotted lines to help you know that you actually went up. What's another way to get to something that looks like it's there? Couldn't I go over and then up and then over and it'd be like on the XY plane? So yes, drawing on a 2D piece of paper to represent 3D objects is going to lead to possible confusion. I just really want to get you to the point where you can see that point really is up from the XY plane. Yes, ma'am.
Can we color code it?
Hell yes. I love my anal students, right? The ones that just have to do everything color pencils, right? I love that. Personally, I would hate me as a student. If I was in my class, I would throw me out so quickly because I so suck at drawing and I don't like color pencils and all that stuff. But if you like them, that's awesome. It makes my job easier to look at your stuff. Yeah.
Can you start with a Z?
Sure. Yeah.
I just want to see.
So coming back up here, if I go up 1/2, so that would be right there. Right? Where am I at? Can you guys see that? There I am. So up 1/2 would be right there, because I'm working with a square here. Then I could go over 1, and then back √3. And it would still get me to about that point there.
I think it's easier to start on the Z.
Yeah, that is.
Cool.
If you
No,
go down
whatever
that
works.
way,
I personally, it doesn't matter which way I start, but if it's easier to start on the Z-axis, I love it, then do it. Right?
It's just so weird because after that I'll look at it and say, I think it's wrong.
Okay. But you will remember having done it, and you will tell yourself, no, me, it's right.
I probably would say that.
I like it. So would I. Okay. That's always a little nerve-wracking for me, not because, because it is something that's just got to kind of click, and even then you realize, shit, I still can't tell.
And then, so we're gonna connect it, and it's gonna be like a.
Exactly. So if I were you, I'm not going to give you a ton of these to do. So if I were you, I'd be even possibly a little more precise. Throw in things that you don't have to know the answer for. Throw in 0.1, 0.2, 0.3, whatever, radians, right? Do you see what I'm saying? Don't just do pi/6 and pi/. Do those, but then throw a few in the middle.
Do you mind
Just so you
drawing
can
the
see how it
actual
goes.
Outcome of the thing.
So this would be,
No, okay, that's
let me do one more so I can see what's going on. If I do pi/4, this of course will be, these will both be √2, and this will be √2/2. So 1.4, 1.4, and 0.7 roughly. So it'll be,
Do you mind zooming out?
of course mine is really getting messed up here now with all the little extra stuff. But I think I've got this point here, and then I've got this point here. See, so it's kind of rising up there. Exactly like we would expect it to, right? Because remember what you said, it should be a circle that's going to kind of rise up as the sine tk piece becomes not 0, and then it's going to go dip down to become less than 0. Yes, sir?
If we were to use a bigger radius, like 4 or 6, would have better.
To say again?
If we were to use a bigger radius,
Oh, a bigger scale. Yeah.
radius, the radius
Okay.
of the circle, instead of 2.
Oh, I see.
Right?
Unfortunately, you can't change the problem they give, but you can change your
The
scale.
picture would be the same.
Sure. So you can change your scale. That's no
So
problem.
you can make one block.
Definitely.
2 blocks equals 1 block.
Anything you've done with XY before, you can do with this obviously because you can do a lot more with this. But you can change your scale to be whatever you want it to be. Each axis doesn't even have to have the same scale. We know that. So if I need my Y scale to be by 5, my Z's to be by 1, you can do that, of course. Yeah. So let's do one more here. This would be, let's see, √2 would be 1.4. 1.4. And now I'm in this block here. Up 0.7. So let's see, I'm 1 point, let me find myself. 1.4. 1.4 would put me like right here in the XY plane. You see where I am? Yeah. So far, I don't mean to put that point. And then I want to go up 0.7. Right? So it's going to actually put me about, let's say I should try to do it the way you guys are saying. Right there, roughly. So I've just gone up a little bit more. Because what's it going to do eventually when it gets to pi/2, and then it's going to start to go back down and around. And I think they have an example almost like this in the book. The one that goes up and then comes back down. They call it the roller coaster curve. Page 724. Roller coaster curve. Yeah. So this is one of those that you just have to really try it out and see how it comes out, right? I mean, you might have to throw away a few graph papers to begin with as you get your process down.
I tried doing it without that and it was awful.
Yeah, without this, it's crazy. With this, it's difficult. Without this, you're crazy. Yeah. So get yourself some of this if you haven't done that yet. Okay. It's obviously pretty simple to do. Just go on Google. Okay. And since you're so nice to let me borrow that, you can have my fridge. Put it up on your fridge. All right. Any other questions from pre-11.6? Yeah.
Could you just give us the answers for the quick quiz, 11.5?
11.5. Oh. Let's see if I put those down.
What defines the difference between a line and a line segment?
Just how they define T.
Oh,
If
it's
T
like
is allowed to be anything, then that line segment's going to be, then it's going to be the whole line. But if T is only allowed to be from 0 to 2 pi or something, you're not going to get the entire thing. Unless it's periodic like this, right? But if you have a straight line, if T is only different, then that's when you get a line segment. So 11.5. So see if this makes sense. So it's B, C, A, CAC, BC. So don't worry. One was B. So that's kind of the question I had up here. You know that's a line segment because the parameter has been contained within a certain domain. Right? So there's, T can only go from -2 to 5, so you're obviously not going to get the whole line forever. It's got to be allowed to go -infinity to infinity to get the whole line. Number 2 should hopefully be a really simple one. Which piece of a line equation tells me the direction, which would really have to do with telling what it's parallel to. Yeah, the one multiplied by the parameter, the T in this case, right? So the 1, 2, 3 is my direction vector. So it's kind of simple then. What would be parallel to that? Well, it would be parallel to itself, 1, 2, 3. Cool. One thing I want you to realize, this should sort of bother some of you, but it doesn't matter. I don't know where the 1, 2, 3 really sits. So that's why I say in general it's just parallel. If it truly sat on itself, even then I consider it parallel, because what's the dot product of something? I mean, what's the cross product of something with itself? 0, right? What does that mean?
Parallel.
They're parallel. So in multivariable calculus, we consider two lines sitting on top of each other to be parallel. Although in algebra we call it, the solution says something different. We say it's not really parallel. But those are obviously going in the same direction. That's all we care about for parallel. They never touch itself. Never touch each other. Let me say that differently. That's not true. But the never touch each other piece of it doesn't really come into play. Right. Number 3. I suddenly had a lot of jokes I didn't want to say. The graph of the function 2 cosine t negative sine t. Now here's the thing. What did we just say? This actually applies sort of like what we did up here. This one comes out looking kind of funky because of the z piece being itself a trig function, right? If in the xy plane you told me that that one we just did was a circle. So if I wanted to pick the entire circle up, I don't want z to be 0, I want z to be 2. So that I can make it cosine t sine t 2. Now the only thing they've done differently here is they say 2 cosine t negative sine t. So that would actually be, it's not an ellipse. An ellipse would require different, truly different coefficients in front of the cosine and the sine. They both basically have 1, right? If it was 2 cosine and 3 sine, that would be an ellipse. Because it's differently, it goes up to 3 and 1, but only 2 on the other. How we doing so far?
How does this look like again?
You tell me now, if it's cosine sine 2, that's basically a circle in the xy plane that's been lifted, so it's parallel to the xy plane. What would this circle be parallel to? And how do you know that? Because it's in the yz plane, and then it's been pulled over to on the x-axis, right? So if I dare it would look like this pull out sitting on 2.
On X.
Yeah. You guys see that? Let me not actually, well, let me see. That doesn't. Thanks. But do you start to see how to look at these functions? That's the new thing for us. We haven't seen like a vector valued function ever before because that's something brand new. It's basically just inputs are, in this case, one parameter. The output's going to be vectors, right? Which actually point to these points that create these shapes. So you start to look at it like, well, what does it look like in the XY plane? What does it look like in the YZ plane? In this case, this is even simpler. One of the things is a constant. So it really only matters what does it look like in the plane that's not constant and then it's been moved over. Oh, maybe. So how would I make one that's on the YZ plane? The XZ plane.
Y constant.
If I want the XZ plane, then I make Y constant. So I can make it cosine t, comma 2, comma sine t, or whatever. That would be in it, pulled out on the Y axis, right? Parallel to the XZ plane. Okay.
How does this next one eclipse? Because the constant's on the end.
Number 4. Now, what is the main thing that tells you an ellipse?
2 and 1.
Because the coefficients are different, which relates to, remember good old x squared over a squared plus y squared over b squared? Or I'm thinking about the general one for hyperbolas and ellipses, right? X squared over a squared plus y squared over b squared equals 1. If a and b are equal, that's a circle. Otherwise, it's an ellipse. And those a and those b's come from these coefficients. Yeah.
Is it parallel to the XY plane?
For number 4? Well, number 1, it's not a circle, so that definitely throws out part A.
Yeah.
But the good question is, what would it be parallel to?
Yeah.
The XY plane,
Yeah.
right? Because now it's been pulled down on the z-axis. Because what's z going to be here? Negative 10. So without that z of negative 10, it's 2 cosine t sine t. It's in the xy plane, nice ellipse in the xy plane, and then I just pull it down by 10. How we do? So if they would have said an ellipse parallel to the xy plane, it would have been answered anyway. Cool.
So that one was what?
4 was C. Sweet. 5. The helix with radius 4 that is coiled about the x-axis. So think about that. If it's coiled about the x-axis, the x piece is what pulls it out. So what if I took the x piece out, it would sit in the what plane? In the y plane. I'm hoping you guys kind of with me. If I draw a circle in the xy plane and I just make z2, I pull the circle up along, and it's around the z-axis, isn't it? So think about, now this is backwards. I want it to coil around the x-axis, right? So I want it to coil around this axis, the x-axis. So that means it's got the basic part of it, if I took the x piece out, it should sit on the yz plane. Okay, so if I took the x piece out, it should sit on the yz plane. Okay, maybe. This is all the stuff about how to start looking at this stuff, how to start picking apart what the graph is going to look like. It's described by which function?
A.
Which one? A is a good possibility, but it's got radius 4, so it's got to be A. What's wrong with B?
2.
It's only got radius 2. And then part C has got 2 problems. It's radius 2,
And the middle.
and it's on the wrong plane to begin with, right? Part C would be on the what plane? Or be trying to if it didn't pull it back out. On the XZ plane. It would be pulled out along the y-axis, right? Okay, so I know 5 of you definitely understand what I'm saying. And the rest of you either don't or you just don't want me to know.
So if it didn't have the radius 4, it's going to be both A and B.
Yeah, if they just wanted a helix
Yeah.
coiled about the x-axis, then it could be A or B. The interesting thing about A is it's got that extra t squared piece, but all that does, of course, it just makes it grow quicker, right? The rate of change as it coils up, it grows itself, right? Are we cool with that? And part B would have a constant rate of change in that direction, right?
Except that would have a radius.
It would be the
two.
same basic shape, it would just be like a spring that somebody's stretching more and more and more, so it's getting further and further apart, the coils, for part A, versus part B, it would kind of go up constantly, because of that T piece. Some of you guys are really starting to see this, which is cool. You gotta realize this isn't that big of a step from what you've done before. You've got to start piecing it out like that. So when I look at 5A, I realize the heart of it is in the YZ piece, right? 4 cosine T, 4 sine T. And all that the T squared does is it pulls that shape along that axis. Okay, so maybe you guys, more and more of you think you're coming on board here. Okay, the rest of you think I'm insane. What about number 6? I love because it's exactly what you hope it would be. Right, so limits work the same way because the components of a vector are just themselves scalar functions, right? I mean, they're just plug in a value and you get a value out. So the math of it should be the same. So you just plug in a natural log of pi over 2, and now here I think there was a mistake.
Yeah.
The closest one was C, but what should it be? Can you guys see the mistake they made? They made it a minus, they made it a negative thing when they really should have made it a inversion, right?
Yeah, one more.
Okay, so maybe some of you guys see that. Because when you plug it in, won't it be e to the negative natural log? Pi over 2. So of course that negative, that e can't kill the natural log until you get that thing out of the way. And of course that thing would turn that over, so overall this becomes 2 over pi. Positive. Cool. So the real answer then for what they have is none of the above. Right? But the closest one is C, and that's actually what they meant.
Who's they?
What's that?
Who's they?
They is the people that made it. Actually, these are not mine.
Oh, okay.
Yeah. Yeah. These are nice. They're just real quick things. I make my own tests and quizzes, but for these things, I just pull them off the little instructor resource thing they have. Yeah.
Okay.
It's kind of nice. Number 7. So now you just got to throw in there infinity. In the last piece, now I don't think in any of those you really need L'Hopital's. You could, because the last one that technically is indeterminate form, right? But of course we use precalculus there. The limit of that's got to be the ratio of the coefficients. That's just one. Of course, L'Hopital would eat that up also. So that's how you end up. E to the negative 3t, where t goes to infinity, is going to die. And then inverse tangent. I don't blame you too much if you forgot what the hell an inverse tangent looks like, but I do if you forgot what a tangent looks like, and then you just turn that stupid thing over, right? Because it just flips around the y equals x line. So if a tangent is like, well, for you guys it's like that, right? Just flip that over, so now it's going to look like that. Pi over 2. So as t goes to infinity, it goes to pi over 2. I like it. Okay. And let me see now. Number 8. The function is continuous. And what's it mean to be continuous? Who remembers the true definition of continuity?
It always has a limit.
Okay. Let's boil it down to being continuous at a point. Because then continuous everywhere would mean it's continuous at every point. So to be continuous at a point,
Define that everything.
the limit
Has to equal.
To exist.
has to exist. I like it. And to really boil it down, if you just say the limit there has to equal the function value there, then that's continuous. Because you're implying that the limit exists, and that there's a function value there, and that those two are equal. So there are 3 parts that I can just make one stupid thing. The limit must equal the function value there. Cool. How are we doing there? So, is there anywhere that could be discontinuous?
Yeah,
You focus your
The pi over 2, 1 over cosine secant.
Yeah, it's got 2 problems. The t to the negative 1, obviously. So it's got to be at least a. But then secant has a problem where?
Pi over 2.
Pi over 2, because pi over 2, of course, secant.
Cosine
Sweet. Like, alright, how are we doing there? So what I really desperately want you to realize is that the math that we've had to do so far is not only nothing new, it's actually decently easy math. It's just that the way the math has been put together is different. And the really nice thing is, for a good long while in this course, that's true. In fact, if you looked at 11.6, which is where we start to get into the calculus of things, finally, in multivariable calculus class. It's exactly the same. Mathematics, right? Cool. So, any leftover questions from 11.5? I think pretty much got it. The thing, and we did a little thing last time about several problems that you could see from 11.5. Find the equation line that goes between these 2 points. It's very similar to what you had to do in algebra. You had to find the slope, which now is a direction vector, and you had to have a point. And they got to give me a point somewhere to go over. Okay. So you can imagine as we go through this class, I can make more and more difficult problems about find the equation line that is where these 2 planes intersect, find the equation line that, so forth. Fill in the blank with whatever new stuff we learned. Right. Because that's what happened in calculus, isn't it? You had find the equation line problems in algebra, and then what happened in calculus? Well, find the equation of the tangent line, and it was the same stupid math, basically, except the first piece you had to do some calculus to get the derivative. And then you do the same y minus y1 business you did before. Okay, so that's going to happen here. Here's the nifty thing about doing derivatives. I want to start with a nice little example that should sound familiar. Just to kind of illustrate what's going to happen here. If I was going 20 mile an hour north, and somebody else is going, what did I say, 15 mile an hour east. After 2 hours, how far have we gone? And how far apart would we be?
40, 30,
So, so after 2 hours, you got 40 miles,
30 miles.
30 miles.
50 miles between them.
And then how do you know that? That's the quick Pythagorean theorem. And really, it could be, it's this officially, but isn't it really the same thing as that if I just want the length of it, right? Are we doing okay there? If I just want the length of it, can I just do this too? That's the same length, right? That's sort of the same thing, just kind of turning the right triangle I'm looking at there. So this obviously would be 50 miles between us, right? And physically it'd be there, but there's a reason I'm putting it there for right now. How does that relate to this? What could I have done here? Instead of, I could do something I did there in a different order. The first thing you did was you multiplied by 2 hours. But what could I do here first? Maybe some of those things. Okay, we can tell what you said. Couldn't I do the same thing before I multiply by 2? How fast are we going? How fast is the distance between us growing? We represent it like this again. So it would really be with this distance here. But how fast is the distance between us growing? 3, 4, 5 times 5 times 5. 5 times 5 is 25. So you just find the multiple. It's a nice little Pythagorean triplet, right? So 25 mile an hour. And of course, multiply that 2. So my point here is, these are derivatives of those, aren't they? This is my velocity and that's my position. So this is really roughly, I want you to realize why this should make sense. It should happen the same way, whether I'm talking about velocities or I'm talking about positions. So if I wanted to look at this and what this here would be. So let's give ourselves a definition here. I'm going to call this just f of t, g of t, h of t. You would hope so, right? So we sort of have to kind of prove it a little bit. So far it's been, and in fact I basically said already that the math is going to be exactly what you hope it would be. It's going to be the same thing. You can do the math on each piece of the vector. We're not going to do this, except for right now. We're just going to look real quick at what this would really be, r prime. If I want to go back, old school this thing, it would have to be the limit. And let's kind of give ourselves a little picture here. Let me just do 2D for right now, just to make it easier on myself. If this is r of t, r of some later time could be here. Let's say I have a, let's say my graph looks like this here. Wow, wow. So there's r of t naught, or let's say r of, let's be a little more specific, r of t plus delta t. Okay, so on the surface, doesn't this feel basically like f of x plus delta x, or h? Remember that in the good old days, right? So I do the same thing. I say, okay, this is going to be the difference between these two. Divided by the delta t. Now notice one immediate difference is I don't have a t-axis here, right? It's not like I have an x-axis and a y-axis and I can see the f of x and I can follow it along. My t-axis is really kind of hidden with just where my position is. I mean, I don't have a t-axis. But that doesn't really matter. It's the same idea. Change the inputs by this much, see what the outputs do, set up the slope, and that's going to take the limit. That's the derivative. We know that that works. But how the hell do you do that? And where would that be on the picture? Where's this represented on the picture? This delta t is just some constant for any given t. Are we cool with that? Obviously, delta t's got to be 5, 4, 3, 2, and you can step in if you wanted to do that to yourself. Where on the picture is this piece then? Yeah, the distance between. So that would be right here. And doesn't that kind of follow what we expect? Right? Because right here, what should the derivative at this point be? It should be pointing tangent to the curve itself. Right? So it's kind of nifty that the r prime, just look at the geometry of it. Once we set up what we know must be true. y2 minus y1 over x2 minus x1. Right? Just in the r and t format. It's the same thing. Looking at the geometry of it, it matches what we hope would happen. We can see our tangent lines start to do. So of course, that's why we have this piece. We let this stupid thing creep in closer and closer like we did in 180. It's the same idea. Let it get in the limit that the delta t is 0. Let it go back and back and back and get right on top of it.
That's the delta R, right?
Oh yeah, well on top here is delta r.
Yeah. So
Yeah. So on the top here, this is delta r. Yeah, cool. So how are we doing so far? I mean, hopefully that makes some sense. Okay. So the funny thing is the math is actually really easy to kind of work with that. I can't work with that. To work with this. In fact, I'm hoping you guys are cool with this. Look on page 729. It's pretty simple what to do with this. I mean, we know that r of t is this f of t, g of t, h of t. So wouldn't this just be f of t plus delta t, g of t plus delta t, so forth? And how do you subtract vectors? Don't you subtract their components? So when I end up with f of t plus delta t minus f of t, can you guys see that? The f piece from here minus the f piece from here, there it is, over delta t. the little limit out front. Now I'm hoping, now let me just stop right there, is that, because what would r of t plus delta t be? What would that be? That would be f of t plus delta t, g of t plus delta t, h of t. So what is that minus this? It would be f of t plus delta t minus f of t, comma, g of t plus delta t, minus g of t. Maybe. And again, this is all on page 729 if you want to. They spell each step out, but I think we get the idea. And of course, what's beautiful about this stupid little thing? That is exactly what? The derivative, f prime. That's the definition of f prime. Sweet. So it is like we hoped. This is going to be f prime of t, g prime of t, h prime of t. That's what r prime of t is. Cool. Now, of course, if I were a student here, I'd just say, well, just say that in the beginning, man. But you have to kind of agree with me and be able to step yourself through, because it's not always going to be true that what was true before is also true now. We have to know, why did something change? Why am I not allowed to do that? Here, the components are exactly just scalar functions. And since everything's component-wise with the operations I'm doing, then I inherit what the components themselves could do. So that's why it's exactly this easy to do a derivative of a vector value function. Crap. So for example, if I have r of t equals tangent t 2 to the t, I'd just be evil by what I give you. T squared minus t. What's r prime of t? Secant squared t.
2 ln of t.
Almost. Derivative of any exponential is essentially itself times the natural log of the base. I like it, and that's why, of course, e is the only base whose itself own derivative, because natural log of e is 1. And this is the nice one. Cool. All right. So this section should be really nice, right? And they can only make it ugly, and they really don't do this too much, by throwing in really disgusting derivatives, quotient rules, and all this kind of crap. But derivatives you gotta love. You can attack them. They're one of the nicest things in mathematics, because no matter what, I can just attack it, right? Even if I forgot derivative of tangent, I can write it as sine over cosine and do a quotient rule, right? Or whatever. So you can always find a way to attack a derivative. Okay, so let's see, anything else to do? Oh, if r prime, in general, if r prime is not the zero vector, then we call r prime the tangent vector. And it's pretty obvious as to why that is, right? It is the tangent at that point. It does do exactly what we expect it to do. So back in 180, we'd have a function like this. At this point, the tangent line would be this. Cool? Now we have our position vector pointing to that point, and we step in this guy closer and closer, but it's always in between. So the closer I get, that subtraction vector is going to point in the same direction it would have if I would have looked at it the way we did in 180. Only now I can have vectors of any size and kind of attack it using calculus. We couldn't do that back in 180. Right? We don't have a nice way to do that. But now I can have vectors that I attack directly with calculus. And they can be in any dimension that I need them to be. Okay. Look on page 732. continue the nice inheritance of things that we've done already. A lot of the derivative rules we've had in the past are the same in multivariable calculus. Are you guys getting Nancy? Just to show you, for example, if I want to do the derivative of u of t dot v of t, or let's just say u, being silly, u dot v. What do you hope that would be? What do you hope you could use? Because this is really a product, and so we want to use a product rule, in this case the dot product rule. And both products that we can do with vectors inherit that product rule. Thank God. So I do the derivative of one. Let me go ahead and give them a little tease. Derivative of one times the other, so that's going to be a dot, plus, leave the first guy alone, Jeff, dotted with the derivative of the other. Or I can put a cross product in there and be the same idea. Cross here, cross, same idea, right? That kicks ass. And of course, those we could prove wouldn't be the easiest things in the world to do. I can't remember if they proved it. Yeah, they do. They proved the dot product rule. A lot of times to prove things with vectors, you break it down to its parts. Why does that make sense? You break it down into u1, u2, u3. Because those parts are normally easy to work with. They're normally either constants or not even linear, just basic scalar value functions. They're like 3x minus 7 or something, right? Or t in there, right? So if you break it down to its parts to prove it, you inherit all the properties of functions, easy functions, right? So if you want to look over the proof of the dot product rule, they break it down to its parts first. And I mean, what is the dot product of u and v? What's the easy one if you don't want to go the angle? u1 v1, u2 v2. And each of these is, remember, u1 and u2 and u3 are not just numbers necessarily now, they are functions of t. But u1 v1 is a product. And we inherit the product rule. Now do you see what I'm saying? So that's why you break it down to its parts, because you inherit everything you know already is true. So vectors are composed of things that we already know everything about. If I just break it down into those parts, I can use all the stuff that I already know. Okay, so if they give it to you, what do you think about this?
3D, that's why this, you wanted to.
Yeah, exactly. This would be three-dimensional. Yeah. Just for an example, if I had, let's do this. What do you think about this here? So what do you think you could possibly do with this? You could do one of two things, and I think what you mean by just plugging in, what do you really mean? Be more specific.
I just plug u of t into
Okay, well yeah, that's a good first step.
You want
Yeah. product rule, and then just multiply it through, right?
Okay, so you could multiply this t squared in, right?
You could use this product rule for the third one.
Yeah, which one?
The f of t, u of t is equal
I
to
like
f
it.
prime of t.
In this case, so that is a product rule, a scalar product rule in that case. Do they call it? They just call it product rule because they're so. It's not scalar though, because this isn't really a scalar, but it's not a vector. The outputs here are scalars, right? If I plug in a 3, I get 9. It's a number. So that I would officially call that a scalar function. So it's like, I would call it a scalar product rule. In this case, what's easier? In fact, in most cases, what's easier? Just bring the stupid thing in, right? Just multiply it in. there's very few cases I can think of where it would be easier to do this and then do that necessarily. Bringing it in here makes it a lot easier because you get a nice t here, right? So you could first bring that thing in. You get t cubed, t squared secant c. Now here you've got to do product rule, right? But here and here you don't. This is just direct derivatives. So you have two different ways you can go about it. You can either make this derivative of this, leave him alone, plus leave him alone, derivative of this, or just bring that thing in there and do the derivative of this. Sounds like when you first learned product rule, they made you do like, pretend like you can't multiply those. Multiply the product, right? You know, like, well, why would I do that? It's the same kind of thing here. I would just multiply that thing in. It's up to you. That was nice. Okay. So you guys want to take a little break? All right, I get that impression. I don't know. Come back 5 till.